Hey guys, welcome back to the part 2 of our Mars Rover functional Scala TDD kata. So today we're going to pick up where we left off. And first, where did we leave off? So let's check our test to see what we have implemented so far. So here's our test file. And the functionality we've implemented so far is we can initialize the rover. The rover returns an error, so it validates the initial heading. Here it validates the initial position. Here it returns a valid state when given an empty list of commands. Here we can have it move forward 1 unit. Our Mars rover can also move forward 2 units when given the forward command twice. Our Mars rover can also produce a valid state when given forward, backwards commands. Our Mars rover can handle being given a left command. Our Mars rover can handle being given a right command. And our Mars rover can handle being given a right and then a forward command. Okay, so basically our Mars rover can do the basics. So looking back at the requirements, we have fulfilled the first requirement. We can initialize a rover that can take commands, right? A rover can take commands. It can go forward, backwards, done. It can go left, right, done. However, these last 2 requirements are what we have to finish today. So let's take a minute to go through them. First, we need to implement wrapping at the edges, but be careful, planets are spheres. Connect the x edge to the other x edge, so 1, 1. So when you are at point 1, 1 on a 5x5 grid, if you go -1 in the x direction, that should wrap you to the point 5, 1. But connects vertical edges towards themselves in inverted coordinates. So for example, so similarly, if you are at 1, 1, and if you go down, if you go -1 unit in the y direction, it connects you to 5, 1. So in this case, if you're at 1, 1 and you go left 1 unit, or if you go west 1 unit, you're at 5, 1. And if you're at 1, 1, and if you go south 1 unit, you're also at 5, 1. So this is pretty interesting behavior. We're going to have to think our way through this so we can implement this correctly. And the last requirement, we also have to implement obstacle detection before each move to a new square. So if a given sequence of commands encounters an obstacle, the rover moves up to the last possible point, aborts the sequence, and reports the obstacle. So I want to keep today's video down to about 20 minutes. Our last video was way too long. So let's see how far we can get in 20 minutes. I believe we can at least implement this, maybe both. So as usual, let's start with the test. And this requirement in particular gives us a very direct test. When starting at 1, 1, make sure if we go left 1 unit, or if we go west 1 unit, make sure we go to 5, 1. So let's write that test. So let's see, so rover, return a rover state, located at 5, 1. When given, so we would have to turn left and then move forward 1 unit. Commands. And what would we expect? Let's see. So it's going to be pretty similar to these commands. So we can copy and paste a few things. So we're going to get to left, and then an F, grab the new state, the new coordinates. We expect this to be located at 5, 1, not 2, 1, and there. Great, I believe this is the test we want. And unlike in our last video where we were kind of manually running each test, like I did just now, we can actually automatically run each test whenever we have a code change. So this test is failing as we expect it to. However, it's going to be a little bit easier for us today if we just do this. If we type the command squiggly or tilde test into your SBT shell, then SBT will actually watch for any file changes and rerun all of your tests anytime you make a change to one of your files. So in this case, our 1 test is failing the way we expect it to. Fail test. Great. Returns a rover state located at 5, 1. And this failed because our rover state is actually at 0, 1. Okay. So that works, and this will be a little bit easier for us. So what we can do, let's make that a little bit smaller. What we can do is to try and get this to pass. Let's go through and see how we would implement this. So just going over what we have so far, we can initialize the rover, and then we could execute the commands, and we're going to fold left over the list of commands, updating the state of each iteration, and updating the state with the return value of the execute function. The execute function takes in an either state and a command. At first, it parses, or it validates the command, and then if it's a valid command, it parses it, and the parse command figures out what kind of command it is. And if it's a forward, it calls move. If it's backward, it calls move. If it's a left, then it'll update the heading directly, and if it's a right, it'll update the heading directly. So inside of the move command is where we are going to have to implement the wrapping functionality. So in the move command, if we have a valid state, then we're going to calculate the new delta. So this doesn't have to change. The delta is the delta, but the update position logic is what's going to have to change. So inside of the update position logic, we're going to have to implement some new things. So we have a new position that we're calculating directly by just directly applying the delta to the current position. So this is where we're going to make the changes here. So instead we'll do something like this. Val, let's see, how do we want to implement this? What we can do is val new position, val unwrap position, val position, let's just call it position. And we're going to write a new function, or we're going to call it calculate coordinates. And this new function is going to take the current position of the state, because in this case, we just have a rover state. We already know that this rover state is a valid rover state, so we're not dealing with monad. This is just directly a rover state. So we're going to take the rover state, and this is stat position, and we're going to pass in the delta, the x delta, and we'll also pass in the y delta. And then this should return to us a new position, and then we can take this, position. In fact, we can just name it new position, a little bit easier. There. And obviously our test is still failing because we have to implement the calculate coordinates function. So this is also part of our private API. Let's see, private coordinates is going to take a position, so P of position, P of type position, and it's going to take a delta x of type int. It's going to take a dy of type int, and it's going to return a position, right? Return a value of type position. And, oh, sorry, of course I forgot the def keyword there. There. Okay, so what are we going to do inside of the calculate coordinates? Well, first, I guess we'll calculate the unwrapped position. So val, let's see, unwrapped position. And for this, we're just going to directly grab the dy. It's the same thing we had before. So we'll have a new position of, let's see, p dot x plus dx. So we're going to create the coordinate tuple in p dot y plus dy. So this gives us the unwrapped position. This was the same logic we had up here a second ago. But then we're going to take this unwrapped position and apply a little bit of conditional logic to make sure the wrapping behavior does what we expect it to do. So we can do something like this. Let's see, and I guess we should probably make this a variable, not a value, because we're going to make this mutatable. We're not actually going to mutate this data, but we might reassign the value, reassign this variable to a different value. So if unwrap position, so we're trying to get this test to pass. This test says if you go turn left and go forward, so if you go west 1 unit, normally the unwrap position is going to be 0, 1. But we don't want it to be 0, 1, we want it to be 5, 1. So if unwrap position dot x is less than map min, or if it's less than 1, then what we want to do is we want to take, in fact, let's rename this to position, and then we'll just reassign this variable position. It's going to be equal to the output of the wrap left, which also just takes the position. And I don't like having hard-coded values inside of our code because 1 has no real meaning. So we should make that map min. And we'll turn that into a constant and pull this constant out over here. Val map min is equal to 1. Let's put this up here. Map min. So our grid goes from 1 to 5. So it's actually a 4x4 grid. It's not 5x5 grid. I may have said 5x5 earlier, but 0 is not included as a valid value within our grid. So then we have a wrap left function. So now we just have to implement this wrap left function and have it return POS, and then this function will return the position. So private def wrap left, and it takes a position and it returns a position. And what we're going to do is the logic of wrap left is actually fairly straightforward. All we have to do to wrap left is take the, let's see, what do we have to do? Is create a new position, and we're going to grab the p.x, because all we have to do is take the p.x, which is 0, and turn it to 5. So take p.x modulo map width plus map width. Plus map width, and then of course pass it into p.y. And I just saved, and we can see our test running automatically, and the test is not passing, so something's off. So the test failed because it should have returned a rover state located at 5.1, but it did return a rover state located at 5.1, but it was headed west. So yes, so I actually wrote this test incorrectly. This should be headed west because we turned left. So I save our test, and the test passes. That's great. All of our tests are passing now. Awesome. So we've implemented wrap left. Let's see if we can implement wrapping along the right edge. So when a rover state returns a rover state located at 1.1, when starting at 5.1 when given the right forward commands. So we're going to initialize a new rover state. So let's do rover state is equal to initialize rover, and we're going to give it an initial position of 5.1, and we're going to give it an initial heading of north, because we always kind of like to have, let's call this initial heading. Yeah, okay, so we're going to initialize a rover state 5.1. We're going to give it the command turn right and then go forward. And then we're going to apply the command, execute the command, grab the new state, and we expect the new location to be 1.1, and we expect the heading to be east. Okay, we're going to save, and let's see if our test fails. Yes, our test fails exactly the way we expect it to, because instead of wrapping along the right edge, it just returns a rover state located at 6.1, which is exactly the wrong behavior that we expect it to be returning right now, because we have not implemented the position. So what we can do here is just add another conditional if else position.x is greater than map width, then position is equal to right position. So you can already see where I'm going with this, kind of following the same pattern. What is wrong with that? No, not if else, else if. There you go. So then we can just implement, let's see, private def wrap right. It takes a position, and it returns a position, and we're going to construct the new position parameter by applying actually very similar logic to what we did previously. So we can just do p.x modulo map width, and then p.y. And that works because when you're at 6, 1, so 6 modulo 5 returns 1, right? Because you can put 5 into 6 one time with a remainder of 1, therefore you get 1, which is exactly what we want. And when I save this, we see that the test passed. That's great. Returns rover state. Our last test that we just wrote is passing. And I hope this text here in the SBT shell is large enough for you guys to see. Maybe I can make that bigger. Well, probably somehow. Let me see if I can make this bigger. Well, let's see. Resize. Let me see. I'm going to move this to the bottom top left. Yes. Is this easier to read? Maybe not. This might not be easier to read. Let's keep this in the bottom then. Let's move this to the bottom right. Yeah, let's just keep it here. That's gonna be a little bit easier to read. Okay, so we have implemented wrap left and wrap right. Awesome. So now what do we have left to implement? We the wrap bottom diagonal. So let's write a new test for that logic. So return a rover state located at 5, 1 when starting at 1, 1. In fact, let me rephrase this. So starting at 1, 1. So rover state should return a rover state located at 5, 1. When starting. No, I think this is phrase. And starting at 1, 1. Return a rover state at 5, 1 when given so just the back command. So we could just like rotate left twice and have the heading go south, or just keep the heading north and go backwards 1 unit. B command. Either works. This seems a little bit more straightforward. So to implement this test, I have to do a few things. So we can use the initialized rover state that we've been using before, right? Just as a refresher, our rover state in our before hook is already being initialized. So we don't have to initialize it unless we want to change the initial conditions. So we can create our commands list. We're just gonna go back one unit, and then we can grab the new rover state, execute commands. And we're going to give it the commands. Let's see, we're going to give it the rover state, and we're going to give it the commands, and we're going to assert that the new coordinates are going to be located at 5, 1, and then I'm just copying this. So we're going to use pattern matching to assert that rover state returns is a right, which with a rover state located inside of it, with a position, which is constructed using the coordinates 5, 1, which is a tuple of int, and we're asserting that it's facing north because we didn't change the heading. Okay, that's our test, and it's failing in exactly the way we're expecting it to. We went south 1 unit, and it returned a rover state in position of 1, 0 instead of 5, 1. So just as a reminder, we are taking this number 5, 1 directly from the requirements, taking this test case directly from the requirements, which is a good way to write test cases. right, so let's see how we might implement this. So if we do something like this, else if position dot y is less than map min, then position is going to be equal to wrap bottom diagonally. Wrap bottom, I guess that's a good way to put it. I mean, I don't really know how, this is a bit weird behavior. Wrap bottom diagonally, or wrap bottom inverted. Maybe inverted is a better way. So it connects vertical edges towards themselves in inverted coordinates. So let's just call it wrap bottom inverted. And this takes a position as its only argument, and it's going to return a value of type position. So let's do. Let's write this down here. So we're going to private def wrap bottom inverted takes a p, and it's going to return a position. And this is going to have this is actually going to have some fairly complicated logic. In fact, we're going to have to take a few minutes to think through this. So how would we do this? So if we're at 1, 1, we go south 1 unit. So so when you're at, let's see, so when you're at 1, 1, and then you go south 1 unit, and you're kind of located at 0, 1. No, sorry, you're located at 1, 0. But we don't want it to be a 1, 0. We want 1, 0. We want this function to turn 1, 0, because this p that's being passed into this function is 1, 0. What we want is this function to convert 1, 0 into 5, 1, which is weird because that means we have to convert both the x. We have to convert this x into a 5 and convert the 0 into a 1. So then how do we do this? Well, the way we could do this could be, well, let's think about this. Similarly, to wrap our minds around this, we could similarly, essentially what we're doing is we're mirroring the bottom edge, right? So if you're at the bottom edge, if you're at the bottom left corner, if you move south, you're going to be transported to the bottom right corner. So similarly, if you're at 1, 2, so if you're in position at 2, 1, following the same logic, then when you go south 1 unit, you'll be at 2, 0, and this function has to convert the 2, 0 into a 4, 1, right? So it has to convert 2 into 4, and 0 into 1. In fact, we just wrote this, so let's go ahead and write a test case for this, because we just wrote out that logic. We might as well write. So starting at 1, 1, so starting at 2, 1, return a rover state located at 4, 1 when given the B command. So we're going to start at, so let's initialize a new rover state over here. Let's see here. So we're going to initialize a rover state located at 2, 1, head north, and we're going to give the back command, and we expect it to return back 4, 1. And let's make sure it fails. We have a compile error, so it's not even failing. Oh, I have a compiler because we haven't actually implemented anything here yet. If we just return P, this will compile. Okay, yep, so our two tests are failing exactly the way we expected them to. It's returning 2, 0 and 1, 0. Okay, so this helps me think through how we're going to implement this. What we're doing is essentially we're mirroring. So we have to find the midpoint of the bottom axes. So let's just do this as I talk my way through this. Let's find the midpoint, valid midpoint. It's going to be equal to, and the midpoint is just like, it's going to be, and we probably need it to be of type float, because a midpoint can be of type integer, but it can also be of type float. It might be a decimal, depending on the length of the bottom axis. If it's only 4 units long, then yes, then the middle is going to be it's going to be an integer. But if it's 5 units long, then the middle is going to be a float, an integer, a decimal. So the midpoint is going to be equal to, pretty straightforward, just map width minus map min. So this is going to be 5 minus 1, so it's 4. And then we just have to divide that in half to get the center. So we have to convert this to a float, because if we try to divide an odd integer in half, then I don't think we get a float. I think we just get back an integer. Plus 2. So this gives us the length of the min width. But then we have to add the map min plus map min. So we get 4 divided by 2, obviously equal to 2. Then we add the map min, because we're starting at 1. We're not starting at 0 the way you would normally do in a normal number line. So the midpoint is going to be 3. 3 in this case. Great, that makes sense. So we found the midpoint, and then what we need to do is calculate the difference between the current x position and the midpoint. Because if you're, for example, if you're at point 1, you are 2 units away from the midpoint, and you're just trying to mirror that across the midpoint. So then we just have to go to the midpoint and then go 2 units past the midpoint, and then that's where you want to be. That's the mirrored value of the x. Val diff. So the difference is going to be equal to the midpoint minus the p dot x. Does that work? And then we're going to take the absolute value. Wait, do we want to? Yeah, because p dot x, because we don't know. This function is should probably be general. It should probably be able to handle when the, right? If it goes from 1 to 5,1, it should also be able to go from 5,1 to 1. Take the absolute value, although that's actually not necessary to get this current test to pass. But that gives us the difference. And then once we have the midpoint and the difference, then all we have to do is actually mirror. So what we can do is something like this, position, let's think. And we can just return position. Let's do midpoint plus diff, and that's a float, so I need to make that 2int, so the compiler is being helpful here. And then we also have to pass p dot y. There. So let's see if this gets our test to pass. No, our tests are not passing. So it's something. Oh, that's because we're not. Yeah, this should be correct. Wrap bottom inverted. Huh. Let's see. Why are our tests not passing the way we expect it to? Oh, because. So we've implemented half of it. So instead of returning 5,1 the way we expected, this function actually returned 5,0. And this function, which we expected to return 4,1, returned 4,0. So once again, this test is really key in helping us implement this correctly. So what we have to do is, instead of returning p dot y, we can instead just return. We could handle this in a couple different ways, but to get this test to pass, we could just hard code 1, but so that doesn't make sense. Instead, we would hard code map min, because when you're wrapping along the bottom edge, you're always going to stay along the bottom edge. You're just moving in the x direction. You're not going to move in the y direction. So let's see if that gets our test to pass. And huzzah, our tests are passing the way we expect them to. We don't need these codes. So we didn't need those comments anymore. And this is passing. This is great. Let's add one more test case. So if we're starting at 3,1, so let's say we're starting at the midpoint, then what behavior do I expect? Well, I think if you're starting at the midpoint, I would expect, given the logic, I would expect us to just stay at the midpoint, because there's nothing to wrap around. There's nothing to invert. So when you start at 3,1, you're going to go to 3,1. Let's see if this passes. And it passes. Great. So our implementation handles that slightly weird edge case. But now let's try and implement wrapping along the top edge as well. So then starting at, so along the top edge is we're going to be at starting at 1.5, return, starting at 1.5, return a rover state at. So we're gonna wrap along the X edge along the top. So located at 5.5 when given the F command. And okay, so kind of similar structure. So we can copy and paste in this code. So we're going to initialize the rover at the position 1.5. So the top left-hand corner. We're going to give it the command forward, and we expect it to wrap around to the opposite top corner of 5.5. And we expect it to still be facing north. So our test is going to run real quick, and it fails exactly the way we expect it to fail. It returned 1.6 instead of mirroring across the top edge. So now let's implement the mirroring across the top edge logic. So then else if position.y is greater than map length, then we'll do the position is going to be equal to wrap top inverted position. So now let's implement this function. Private def wrap top inverted, and we can do p. It's going to take a position. This is going to take a position, and we're actually the logic is going to be fairly similar. In fact, we probably don't need two separate functions. We could probably combine this. Yeah, we can actually combine this into one function, because really all we're doing is, the only thing that has to change is this, the y value. Wait, does it? No, well, actually a few other things have to change. Yeah. In fact, let's begin. Let's just refactor this, and instead of calling this wrap bottom inverted, let's just call this wrap inverted, and let's refactor this to actually work generally. So let's say okay, let's make it take two arguments. So wrap inverted is going to take the y position, and it's going to be a type int. So in this case, the y position is going to be, so when we're wrapping along the bottom edge, we want the y to be equal to map min, and when we're wrapping along the top edge, we want the y equal to be map length. So that gives us the y. So let's make sure our previous test passes now that we have this change. So we're just going to implement this y. So we saved, and actually all of our tests are passing. Hey, that's great. I didn't even think our last test was going to pass with that change. That kind of surprises me, but I'll take it. Usually when something happens and you didn't expect it, that probably means you need to go back and write a couple additional tests until you really know what's going on. So that's what we're going to do. So what did we just do? Let's go over that real quick. So whenever the y is less than 1, we call wrap inverted, and we pass it map min. So it's going to take the position, and it's going to grab the midpoint, grab the diff. That's straightforward. That hasn't changed at all. But it's just going to return. It's going to wrap along the center of the x-axis, and it's going to pass in, and the y is going to be equal to the y that you passed. And yeah, that makes sense. That totally makes sense why this test is passing. Let's write one more test to make sure this passes the way we expect it to. So starting at 2.5, return a rover state at 4.5 when given the F command. So 2.5, 4.5, and let's see, is that going to pass? Yeah, it passes. Okay, so I think we're done with this requirement, but I think we should take a step back and think about this for a second. this logic works, but it only works with the current configuration of a 4x4 grid. No, yeah, if it's a 4x4 grid, from 1 to 5, 1, 2, 3, 4, 5. Sorry, it's a 5x5 grid. What am I talking about? Sorry. It's a 5x5 grid with a 3 is the center. So that makes this math work out pretty well. So we can divide by 2. We can just divide by 2, and this gives us, it gives us a float, but it's a whole number float. And this takes care of allowing us to wrap in both directions. And this, let's see, does this work? Let's think. If p dot x, is there any weird conditions, weird situations where this might not work? There's some inkling. I've got some inkling that maybe there's an edge case here that I'm not testing. You should always kind of follow these instincts. Let me think this through. If the midpoint, if x is less than the midpoint. Okay, so what we're actually then missing, so thinking about it, we are missing a test. And I was right. So the test I'm missing is that all of these tests start on the left-hand side of the midpoint, and they're mirrored over to the right-hand side of the midpoint along the bottom or the top edge. However, if we write a test that starts on the right-hand side of the midpoint, so starting at, for example, 5, 5, return a rover state at 1, 5, when given the f command in and we can write this. So starting at 5, 5, given the command f, expect it to go to 1, 5, because we expect it to be able to wrap along both from one side to the other, regardless of the starting point. And if we do that, this test fails. And it fails because it just returns back 5, 5 instead of returning back 1, 5. So let's track down why this logic isn't working. So wrap inverted, when it receives a position at 5, 5, and it receives position, so the y is correct, so we don't have to worry about the y. The y should be 5. But when it receives position 5, 5, it calculates the midpoint of 3. It calculates a diff of 1, a diff of 2, because 5 is 2 units away from 3, and it just returns back 3 plus 2, which is 5. So that's obviously incorrect. So what we want is we have to add a little bit of conditional logic here. So instead what we can do is something like this. If p dot x is less than midpoint, then what we want to return is return position of midpoint plus the diff dot to int and y. And of course I messed that up there. And similarly, if p dot x is greater than the midpoint, then return the midpoint minus the diff. So that would be, which is what we want in this case. In this case, p dot x is y, p dot x is 5, the midpoint is 3, and what we want is we want to take the midpoint 3 and subtract 2 in order to mirror it to the other side and return 1 as the new x value. And similarly, and we can do something like this. Else, and we actually don't even need this. There, else position, and we don't need that. Let's test that. Does this work? Let's see. This is having trouble. Wait, yeah, that passes. That works. And that return statement was redundant because in Scala, everything is an expression. This is not a statement. So the entire if-else block is one expression that returns a value. So you actually don't need a return clause inside there, unless you want to early return at a different point inside of the function. Okay, so this expression either evaluates to this or evaluates to that. Let's try one more test to make sure that this works along the bottom edge as well. So let's see. So starting at let's see, starting at 5.1. No, starting at 5.1. Return a Rover state located at 1.1 when given the back command. So starting at 5.1, given the command back, return 1.1, still head north, and the test pass. Okay, now I think I'm confident that we have correctly implemented this second requirement, with the caveat that this should probably be a little bit more flexible, more user configurable. Okay guys, next time we'll implement the last requirement. See you next time.